Okay, good morning. I guess we'll go ahead and get started. It's about 8:35. Okay, so let's just sum up where we're at this point on the syllabus. And so we're at our fourth meeting, and so we have this one and one more in 2 weeks, and that'll be our last one. And so let's see. So I graded all your homeworks that were due last time. So you should see a grade for the elasticity homework on Blackboard. You should see a grade for homework 4, and you should see a grade for homework 5. Okay, and I posted my solutions for all 3 of those assignments. So there's solutions and grades for all the homeworks 1 through 5 and the elasticity homework. So look at the solutions if you missed any points. If you have any questions about those assignments, please let me know. So all your grades are out for those, and all the solutions are posted on Blackboard. Okay, and then today, you have 2 assignments due, one being the midterm. So I've already gotten a bunch, if not all of those, via email. So if you've not emailed me your midterm exam answer sheet, make sure you do that by the end of today. So I guess you have till midnight tonight. So make sure you get me your midterm if you haven't done so already by today. And then also the homework for Chapter 8, is due today, so that goes on Blackboard. Alright, and so once I get all of those submitted today, I will get your grades in at some point before next meeting. And so, yeah, that's where we are. And then today, we're going to, not doing that. Today, we're going to do Chapter 9 in your textbook on some oligopoly models, and also Chapter 10 in your textbook on game theory. So a whole day of oligopoly. All right, and then next time, you'll have the Chapter 9 homework to do, which we'll review today, and the Chapter 10 homework. So that's kind of where we're at. You're past the midway point as soon as you turn your midterm. And we've got 2 more chapters to do today, and then again next meeting will be our last one. And we're gonna the final 2 assignments will be the oligopoly homework and the final, which we'll talk about next time. Okay, and so next week's meeting will be another review of the exams. We'll do a practice exam for the final, and then we'll also talk about the oligopoly homework. Okay, so I don't think next week's meeting will be 4 hours. Might be a little bit shorter. Today's will probably be about the same, the average time, but next week's last meeting might be a bit shorter because we have a couple of things to do, but no new chapters. All right, and then just make a note that you have a little less time to do the last 2 assignments because I want to get your grades in by the 15th. And so assuming that you guys get the final exam and the oligopoly homework into me by Thursday, August 13th, I will have all your final grades submitted, and I'll post it on Blackboard as well. But your grades will be done if I get everything in on time by August 15th. Okay, so if you can get the last 2 assignments in by the 13th, I'll have all your grades in by the 15th. Okay, and then you can take a break and focus on the fall term or semester, which it looks like that's going to be online as well. Are you guys taking fall courses online at Laverne? Okay. Yeah. So And from what I've been informed, it looks like those are going to be remote as well. So I hope that goes well. But I think we'll be doing Blackboard and WebEx and Zoom. Okay, so today we got Chapter 9 and Chapter 10 to do. Any questions on the past homework? Anything up to this point, or just general questions before we start today's new material? Okay, so everybody seems up to date. I think I've gotten most of your midterm exams via email, and then make sure you also have to turn in the Chapter 8 homework today if you have not done so already. So those two things due today, and before next time I'll get your grades for the midterm for the homework Chapter 8 and my solutions. Yeah, so I got a few more of those need to get in, but that shouldn't take you too long. And so, okay, I know a few students have, like, if you want to update your homework and, you missed something or you want to add a new one, I've seen some students add a second post, which is completely fine. And so if you miss something or want to add an updated homework, you can just post it again. So you don't have to let me know, but just I'll grade the most recent one. And so if you've posted two things, I'll just look at the most recent one. So it's no big deal if you post more than one time to the discussion board. All right. So let's start for the first session. We'll start Chapter 9. And this will be on some oligopoly models. And so let's go ahead and get prepared for this one. Okay. And also, everybody's good on the midterm, which is due today, right? So I think I've got most of them. But if you have any questions on that, please let me know as soon as possible because that's due today. All right. So I'm going to open up the Chapter 9 section, the Chapter 9 Word document, and the Chapter 9 homework, which we'll get to a little bit later in the early session. And if you want to open up the Chapter 9 PowerPoint, we'll start with that. Okay, so just to review, we're covering in the last few chapters, we're covering the four basic types of market structure that we're going to look at. We're going to spend the most time on this one, the oligopoly structure. And so let's just review where we're at. So we did the last three types. All right, so I believe that last week, or not last week, but 2 weeks ago, our last meeting, we covered perfect competition, monopoly, and monopolistic competition. And all of those were part of your homework that's due today. And then Chapter 9 and Chapter 10 are both on the fourth type of market structure, which is oligopoly. And so we'll look at this type of market in a lot more detail in Chapter 9 and Chapter 10. Yeah, it's a difficult word. So. All right. So Chapter 9, basic oligopoly model. So here's an optional video on game theory, which we'll talk about more in the next chapter. All right, so you're probably somewhat familiar with this type of market structure from Business 500B or some other econ course. But an oligopoly market is a market structure in which there's only a few firms, and each of which is large relative to the industry. And so this is the type of market where it's not monopoly, but there's a few, usually like less than 10. And all of those firms are usually very large, and this is, so examples of oligopoly market are a lot of the electronics and tech industry. Okay, so you're probably familiar with the big brands, and these are just some examples, but these are some main ones that are looked at a lot. So smartphones, cell phones are definitely now a big oligopoly market in which you got Apple, and you got Samsung, and you got a few other ones, but there's only a few big competitors, and mostly I'd say that Apple and Samsung have a majority of the market. Your video game console market is consisting of pretty much three big firms, if I'm not mistaken. You have the PlayStation, which always is competing with a new version. You have the Xbox, and you have the Nintendo, which usually comes out with something. And to the best of my knowledge, those are the three big oligopoly firms in that market. And then this is becoming even more competitive, the streaming service market. And so I'm not sure exactly how many there are, but each of these firms or companies is relatively large, whether it's Netflix or Amazon or HBO or Disney or whatever else is next, Peacock, NBC. But there's probably around 10 now, but each of these big oligopolies is trying to compete in this big streaming service market. This is becoming a much more competitive market by the day. All right, so those are some examples. We're not going to do this first type, so skip to slide 5. All right, so skip a couple slides to slide 5, and we're going to start with the first type of oligopoly model or type of modeling structure that we're going to talk about, which is the Tourneau oligopoly. And so this is a subset or a type of oligopoly, basically in which you have oligopoly firms that have the same amount essentially a market power. So we have a few firms serving many customers. That's standard. They produce a differentiated or homogeneous product. That's standard. The big difference here is that each firm believes that rivals will hold their output constant if it changes its output. So they model their output decisions based on what the other firm's going to do, but they don't think that they're going to respond to their output changes. So this is a type of market in which both firms are competing, kind of have the same amount of market power, but they choose their output based on the other firm's output, but don't assume that there's going to be a response. So we'll look at the mathematics of this model, but the three examples I showed you, I think the one that would be the most representative of Cornell, I think would be probably the video game console market, because we can look at two firms. So as a real world example of Cornell, the best thing I can think of that's based on these three examples is the video game console market, where you have the Sony PlayStation model, which keeps getting updated, and also the Microsoft model. And then you also have Nintendo, and you have like PC games. But I think I would think that those are the two biggest competitors in the video game market. So I don't really play video games anymore, but would you guys agree that those are the two main players in the video game console market, and they probably have the equal share of the market? Okay, so let's use that example, and I think so the thing is they're both very. I mean, the game makers make games for both types. The consoles are pretty much, every time they come out with a new model, it's pretty much the same price, and so they're really just going for like who prefers one or the other. I'm sure one of the types has like they like playing this game on this system or et cetera. I'm not even sure what the difference is in terms of like what the consumers prefer for each, but they're very similar and they're very big competitors. And it doesn't seem like and so barriers to entry exist, which means it's very hard for another market to jump in and compete with these two. And so I think the PlayStation and the Xbox have been, very big competitors for almost 20 years now, and so it's very difficult for another company or type of product to come in and replace or compete with these two. All right, so any competitor has to do something kind of niche, like make a PC game, or Nintendo does the Wii, or does goes old school and does the Switch. But in terms of just new games and new technology, these two are the big competitors. Okay, so we're going to look at kind of a mathematical model of an example of the Cornell, which again would be in one example the video game console market. There's probably other ones you can think of, but let's stick with that one. So we're going to develop or define a best response function. So we'll stick with two terms. And a best response function is a function that defines the profit maximizing level of output for a firm for given output levels of another firm. So we'll have a model with two firms, firm one and firm two, One for this example can be Sony, one could be Microsoft. So you can apply it to other companies as well. But let's look at what the reaction functions look like when I'm on the same graph. Alright, so if we look at figure 9.3 in the PDF textbook. Alright, so there you go. You see two firms, two Cornell oligopolists, and then on the y-axis is firm 2. Here's her output, which is Q2. Alright, and the other firm is output Q1. So these are both the firm's outputs on the same graph. Alright, and you can see that each firm's output decision is based on also what the other firm would choose as output. And so what we get is here's firm reaction function of firm 1 here. So that's what that firm would choose based on the other firm's output, and this is the reaction function of firm 2, which is the reaction function of firm 2 based on firm 1's output. Okay, and what you see is because both these firms essentially split the market, that they're going to choose basically the same level of output, but it's going to depend on their cost structure. And so we get a point something like there, where firm 1 chooses Q1 star based on firm 2's output, and firm 2 chooses Q2 star based on firm 1's output, but they're essentially choosing the same because they're kind of splitting this market. Alright, so that's kind of what it looks like on the graph. We're going to look at an example of how these firms make decisions based on just two oligopolists, basically splitting the market, and this is kind of what Sony and Microsoft do. It really depends on how they can get the cost down and what the other firm does. Alright, so let's look at our first example, demonstration problem 9.4. And I did this on a separate Word document. Alright, so I put a little definition or summary of the Cornell oligopoly I got from a web search, so you can look at that. And there's a little web link. So this defines, or just talks about or defines some more about the Cornell, and then what some more real world examples. So you got another example they proposed of a real world example of the Cornell style is the OPEC countries, the oil producing nations that kind of agree. And so the thing is there that they don't really they all agree on output, and then the price is set based on that. So if one firm changes its output, they don't change it because they all agree upon a certain amount of output. So that's a bigger example where you got a bunch of firms that don't change output based on the other firm's output. They make output decisions in unison, and then that together determines the market price. So that's a bigger example, kind of an international Cornell, is all the OPEC countries, how they make decisions based on output. All right. And then you got some optional videos on just intro to oligopoly, some more on Cornell and Stackelberg, which we'll talk about. So there's a couple videos you can look at. You can look at this description of the Cornell and that web link. if you have time later, but let's do now the first demonstration problem 9.4. Alright, suppose the inverse demand functions for two Cournot duopolists is given below. And the costs are 0. So here we go. We got two firms, firm 1 and firm 2. You can think of these as our continued example of Sony and Microsoft. So this is the demand function based on the two together. Okay, so price is 10 minus Q1 plus Q2. Alright, so this is a demand function we're familiar with, but now we have two firms. So like you did in the homework, you had a demand function which was like, for all the other markers, there was some number, 10 minus Q. And the only difference here is we now have two firms, both in the same demand function. So price is determined by the output of the two firms together. So here we go. First, you can calculate part A, what is each firm's marginal revenue. And so you've done this in your homework for one firm. The only difference is we have two firms. So the revenue of firm 1 is its price, or the market price, times its quantity. So the price of this game console, whatever it is, that's set by the market, and then times Q. So, revenue is price times quantity. That's price from the demand curve, 10 minus Q1 minus Q2. And then Q, or Q1, is the quantity of firm 1. So this is price, this is quantity. And therefore that is firm 1's revenue. Alright, so just multiply the Q1 through, you get R1, revenue of firm 1, equals 10Q1 minus Q1 squared minus Q2 Q1. And then you know that the marginal revenue is just how that changes on the margin with respect to Q1. So MR1 is just the derivative of this with respect to Q1. It's the same exact thing you did on the homework, except we have two firms. So DR1 DQ1 is MR1, which is equal to 10 minus 2Q1 minus Q2. Alright, so the only thing you're differentiating here is Q1, Q2 is constant as far as the firm 1 is concerned. Alright, that's the MR, the marginal revenue function of firm 1. And you should, when you do this example with the Cournots, you should get, if you do it side to side like I did here, you kind of get the same thing for both firms because it's kind of symmetrical, knowing they're going to split the market. And so you should get firm 2's MR function, which is this is kind of the same thing, but from that firm's perspective. Alright, so at R2, the revenue of firm 2, do it the same way, price times that firm's output, use price, 10 minus Q1 minus Q2 times Q2 for quantity. Then distribute the Q2, you get 10 Q2 minus Q2 squared minus Q1 Q2, and then just differentiate that with respect to Q2 to get MR2. Okay, so you get 10 minus 2Q2 minus Q1. And you can see that both MR functions are similar, but it's kind of from the other perspective. So you get 10 minus 2Q1 minus Q2, and from 2 you have 10 as 2Q2 minus Q1. So you should see the symmetry if you do this correctly. Okay, B. What are the reaction functions for the firm 2s? And so the reaction function is simply you want to use your profit maximizing condition. All right, so remember that's your profit maximization condition. You did that in the homework for chapter 8. The only difference here is we have two firms, so it's going to be like MR1 equals MC1 and MR2 equals MC2. Okay, so that's the reaction function. It's their profit maximizing condition, and it should be a function of the other firm's output. All right, so here we go. Let's start with firm 1. Okay, so MR1 equals MC2. That's firm 1's profit maximizing condition. You just calculated MR1, 10 minus 2Q1 minus Q2. And this is a simplified example of which there's no cost. And if there's no cost, there's no marginal cost. So normally there's going to be a cost function, but here for simplicity, just to get the idea, there's no cost. So if there's no cost, there's no marginal cost. So MC is 0 because cost is 0. So set MR1 equal to MC1. So MR1 is that, 10 minus 2Q1 minus Q2. And MC1 is 0 because there's no cost. Okay, and then all you have to do is solve for that firm's output as a function of the other firm's output. So you want to find Q1, because this is firm 1, as a function of Q2. And that is firm 1's output choice based on the other firm's output, its competitor, right? So this would be like Sony's output decision based on Microsoft's output as well. And then that, we call that the reaction function. Since this is firm 1, just solve for firm 1's output, Q1. So we get, put the 2Q1 on the other side. 2Q1 equals 10 minus Q2. And then just divide by 2. And you get Q1 equals 5 minus 1 half Q2. So that is firm 1. Reaction function, you do the same thing for firm 2. But you should get a result that gives you something, the same thing, but from the other perspective. Alright, so here's firm 2's analysis. So same thing, MR2 equals MC2. MR2 is 10 minus QQ2 minus Q1, and MC2 is 0. Take Q1, add QQ1, add QQ2 from both sides, you get 2Q2 equals 10 minus Q1, and then just divide by 2. And you get 5 minus 1 half Q1. So you see you get both firm, this is firm 2's reaction function. And so see the symmetry. Firm 1's reaction function is 5 minus 1 half Q2, and firm 2's reaction function is 5 minus 1 half Q1. So that's what each firm's optimal output choice based on the other firm's output. Alright, so this is if whatever firm 1 does with Q1, this defines what firm 2 is going to do, and so forth. So they both have a function in which their outputs depend on each other. And so that's why you kind of see that the only thing that really determines output is the cost and the market price. Okay, part C. What are the Cornell equilibrium outputs for the two firms? Alright, so this part's just a little bit of algebra. All you have to do is you got these two functions. Alright, so you got Q1 is a function of Q2 and Q2 is a function of Q1. And you know that if you have two equations with two unknowns, to solve for the variables, just solve for one and then solve for the other. So this is like if you had x as a function of y and then y is a function of x, to find both the variables, just put one into the other and then solve for that and put that into the other. So let's first put Q2's reaction function into firm 1's reaction function. Alright, so we have Q1 equals 5 minus 1 half. And so Q2, all we're doing here is putting this into there. So Q2 goes in here, and that's what we're doing here. So we're just plugging Q2, firm 2's reaction function into firm 1's reaction function. So we get Q1 equals 5 minus 1 half times 5 minus 1 half Q1. So now we have just Q1, and all you gotta do is solve for Q1. Okay, so we get Q1 equals 5 minus 5 halves plus 1/4 Q1. Okay, and then if you subtract 1/4 Q1 from both sides, you get 3/4 Q1 equals 5 minus 5 halves is 5 halves. And then just multiply both sides by 4/3, and you get Q1 equals 4/3 times 5 halves. And that simplifies to 20 over 6. Which is 10/3. Alright, so now for firm 2, I guess the easier thing to do would just be to plug in 10/3 here. But I did it the other way, so you can do it either way, I guess. So I plug in firm 1's reaction function into firm 2, and you kind of get the same thing, or you should get the same thing, where you get 5 minus 1 half times 5 minus 1 half Q2. Now we just have Q2. So we get 5 minus 5 halves plus 1/4 Q2, and then subtract 1/4 Q2 from both sides, we get 3/4 Q2 equals 5 halves, and multiply by 4/3. We get 4/3 times 5 halves, which is the same thing, 26. Which is 10/3. So if you do this Cornell analysis correctly, you should get the same output for both firms because they both split the market. Alright, so you get Q1 star is 10/3, Q2 star is 10/3. The last part is easy here. What's the market price? Alright, all you have to do is plug in Q1 and Q2 into the demand function, and then find out what the price is. Alright, so there is the demand function, 10 minus Q1 plus Q2. So you get 10 minus 10/3 for Q1, minus 10/3 for Q2, and then if you solve this, it doesn't come out super nice, but 30 thirds minus 10 thirds minus 10 thirds gives us 10 thirds. So P star is 10 thirds. Alright, so that's our first example of the Cornell analysis. Any questions on what we did here? Alright, so we have another type of market to look at, which is the Stackelberg. So let's go to slide 7. Okay, so I'm gonna refill my coffee cup, and then we'll do this one in a second. So just give me a minute. Okay, so Stackelberg is another type of oligopoly we're going to talk about and analyze. And so it's a little bit different. Here's the description. So there's a few firms serving many customers. That's standard for oligopoly. Firms produce either differentiated or homogeneous products. That's pretty much the same for all oligopolies. The big difference, which defines this model, is items 3 and 4. So you have a single firm, a leader, which is going to choose output first before the rivals choose their output, and then you have followers which take the leader's output given, and then they select their outputs that maximize their profits based on the leader. All right, so there's a leader and a follower, and they don't simultaneously choose their output based on the other firm. One firm goes first, which has a little more market power, and then the other firms go next. Okay, and there's always barriers to entry in oligopoly because it's hard to penetrate this market because of the current market power that the firms have. All right, so let me try to use one of the other examples for, well, here, I have a description. Okay, so if you know the Word document, I put a little piece on the Stackelberg, which you can look at. And so here's some more descriptions on Stackelberg. Their real world example of a possible Stackelberg model is this one. Would be Microsoft's dominance in the software market. And so there's other firms that make software, but you can definitely see that the software market is probably dominated by Microsoft. And so most of a majority of the software is, Microsoft Office, Microsoft Word, Microsoft Excel. And there's other firms that make, word processing things, and there's other firms that make spreadsheets. But I'd say that the leader in this case of the software market would be Microsoft. So Microsoft will be the leader here for our example. And then we'll just pick another firm as firm 2 being the follower. And so now, I don't know, what's software? So what's another big firm that, or big company that makes software? Adobe? I'm not sure if that's the same level, but, maybe like Google Sheets. Yeah, so maybe we can do that. Maybe we can say like the software, the spreadsheet software market, where you have, okay, so maybe we can use that. So I think this will work as an oligopoly, or the Stackelberg oligopoly, where it's clearly the biggest spreadsheet maker. Software terms is Excel. That's the standard practice for any business, but yeah, you can still use Google Sheets and do some of the analysis. So we'll say that a majority of the market, the leader, is going to be Microsoft because they make the majority. They have the majority of the market in the spreadsheet market. But we'll have a follower, and be Google Sheets. I'm not even sure if there's a third option. But let's use those two. Okay, so here's a little further description on Stackelberg. You can look at this. And there's a couple web links that talk about Stackelberg. All right, so we'll do a demonstration problem for Stackelberg. We'll use, for this example, we got Microsoft Excel being the leader and then Google Sheets being the follower. And let's look at demonstration problem 9.6, which I did on the other document. All right, so everybody doing okay so far? Ready for another example?
Yeah, we're good.
Okay. All right, here we go. So this is demonstration problem 9.6. We'll propose the inverse command function for two firms in a homogeneous product Stackelberg oligopoly. And the cost functions are given below. So firm 1 is the leader. We'll say firm 1 is Microsoft making Excel. And firm 2 is the follower. We'll say this is Google making Google Sheets. Okay, and so just note that all of these models are simplifications, which we really have the same cost structure for both firms. So all of our examples assume the firms have identical cost structures. Now, in the real world, probably because Microsoft's been doing it longer, they can cut their costs a little bit lower for spreadsheet making than Google, but for simplicity, just assume they have the same cost structure so we can do the analysis. Okay, firm one's the leader, firm 2 is the follower, here's the main curve. 50 minus Q1 plus Q2. Here's the cost function of term 1, which is 2Q1, and here's the cost function of term 2, which is 2Q2. Okay, so for the similar analysis, but the major difference, which makes it slightly more complicated, is term 1 goes first, term 2 goes second. Alright, what is term 2's reaction function? And so the reason why we're solving for only term 2's reaction function is because term 1 doesn't react, it goes first. So the only term that reacts is term 2, so that's why we got to find term 2's reaction function. But there is no reaction function of term 1, it just does what it wants first, and then term 2 reacts. So we'll do this in the same way. Find the revenue of term 2, okay, price times its quantity, 50 minus Q1 minus Q2 times Q2. Distribute the Q2, we get 50 Q2 minus Q2 squared minus Q1 Q2, and then differentiate that with respect to Q2 for MR2, and you get 50 minus 2Q2 minus Q1. Alright, and then term 2's cost is 2Q2, and to get the MR of that, just differentiate that with respect to Q2. This is easy, but it's just MC2 is 2. Okay, so you got MR2, you got MC2. To get term 2's reaction function, just set the two equal and solve for Q2, because term 2's reaction function is Q2 as a function of Q1. Okay, MR2, 50 minus 2Q2 minus Q1 equals MC2, which is 2, and just solve for Q2, so you get 2Q2 equals 48 minus Q1 divided by 2, you get 24 minus 1 half Q1. Okay, so that is term 2's reaction function. And then part B is what is term 1's output. So what you want to do here is define term 1's profit function, and then plug term 2's reaction function into term 1's profit function, because term 1 is going to maximize profit based on what term 2 is going to do next. Okay, so profit is revenue minus cost for term 1, and revenue is just price times quantity. So the price is the banana curve, 50 minus Q1 minus Q2 times Q1, and then minus the cost function, which is 2Q1. Right? So you can simplify this a little bit. 50 Q1 minus Q1 squared minus Q2 Q1 minus 2 Q1, and then just combine the Q1, and you get 48 Q1 minus Q1 squared minus Q2 Q1, and then the next step is to plug in term 2's reaction function, because term 1 wants to choose its output based on what it calculated that term 2 will do as a follow-up. So just plug in term 2's reaction function into Q2. So that goes here. Alright, that's what we're doing now. 48 Q1 minus Q1 squared minus Q1 times Q2, which is going to be term 2's reaction function. 24 minus 1/4 minus 1 half Q1. So we get 48 Q1 minus Q1 squared minus 24 Q1 plus 1/2 Q1 squared. And then the next step, it simplifies nicely to output of firm 1 is 24 Q1 minus 1/2 Q1 squared. All right, so it simplifies to something a little easier. And then the next step, let's maximize profit for firm 1 by choosing Q1. And that's the profit function. Let's maximize that choosing Q1. And so all you're doing here is differentiate the profit function with respect to Q1, and then set that equal to 0, because this is kind of when the peak, when it changes is equal to 0, that's when it's hit the peak. And so when profit hits its maximum, that's when the slope or the derivative is 0. So that's the context here is differentiate profit, and when that equals 0, that means it's hit its maximum point, and you want the Q star that identifies that. So differentiate profit 1 with respect to Q1, and just set it equal to 0, and then find that Q1, because that's when profit reaches its highest point. So it should simplify here nicely, where we get differentiate that with respect to Q1, and we get 24 minus 1. So 24 minus, so you get, this Q comes down, and minus 1, so we just get 24 minus Q1, and set that equal to 0, because you want that's the change, the slope to equal 0, because that's when profit at its maximum point. And all you do now is solve for Q1, and Q1 star equals 24. Okay, so for the Stackelberg, finding firm 1's output is probably the most tedious part, but we've done that now. So again, what we did here is find firm 2's reaction function, define the profit function of firm 1, and then maximize profit for firm 1, the leader, based on integrating firm 2's reaction function, because that's the best firm 1 can do. So we did that. Now the rest of it's pretty easy. Part 2. What is firm 2's output? So all you have to do now is plug in firm 1, the leader's output, into firm 2's reaction function. So here's firm 2's reaction function. We know that firm 1 is going to choose an output of 24. So 24 minus 1/2 24, and we get 24 minus 12, and so the output of firm 2 is 12. So you can see that firm 1 gets exactly half of what firm 1 got. Okay, and so firm 1 chooses 24, firm 2 chooses 12, and so that's the best that firm can do based on having a leader of Microsoft. Okay, so what's the market price? Just plug in the output function, or the output decisions into the main curve, which is 50 minus Q1 plus Q2. So 50 minus Q1 star is 24, minus Q2 star is 12, and we get a price of 14. Alright, so for the Stackelberg, you should see that firm 1's output is double firm 2, which essentially means that firm 2 gets a third of the market, and firm 1 gets 2/3 of the market. So there's a big difference when you have a firm that has a lot more market power and is a leader, such as what you most likely see in the spreadsheet market, where Microsoft has probably 2/3 of it, and maybe Google Sheets has the other third. There might be some spreadsheet software that I'm unfamiliar with, but I think there's a bit too in the spreadsheet market. All right. So that's our first example of the Stackelberg leader follower example. Any questions on what we did here? Okay, so let's see. Okay, so those are the main two models I want you guys to know for chapter 9 for these oligopolies. We got the Cornell type, like the game console market, where they kind of split the market, and you have the Stackelberg, like the spreadsheet market, where you have a leader and a follower. You can probably think of many more examples for both types, but understanding the model is the most important thing. And so we're going to look at one more big example, which we compared it to. So we'll have the same demand function, the same cost functions, but let's analyze it for both the Cornell and the Stackelberg, and you can see the difference here when you do the analysis kind of side by side. So let's compare the oligopoly models on page 290 by analyzing it from the Cornell perspective and then the Stackelberg. Okay, so go back to the Word document. All right, so what we're going to do here is we're going to compare the two types. So to see how each of the forms of oligopoly affects firms, it's useful to compare the models covered in the chapter in terms of individual firm outputs, prices in the market, and profits. So we're going to use the same market demand and cost conditions for each. And so here's the inverse demand function and the cost function. And so what we're going to do is look at Cornell for this one, and then solve for the outputs of both firms, the profit of both firms, and then the market price. And we'll do the same thing for both firms from the Stackelberg perspective. Okay, so here we go. Here's the demand function. Price is 1,000 minus Q1 plus Q2. And here all the cost functions are for QI, so that means it's, firm 1 is 4Q1, firm 2 is 4Q2, and so on. So start with Cornell, and let's go ahead and we're trying to find the outputs and the profits and the market price for this market. So we have to define the revenue functions. First we have to get marginal revenue and marginal cost and set those equal for each firm. Okay, so the revenue of firm 1 is price times its quantity, which is 1,000 minus Q1 minus Q2 times Q1, and then distribute the Q1. You get 1,000 Q1 minus Q1 squared minus Q2 Q1, and then if you differentiate that with respect to Q1, you get 1,000 minus QQ1 minus Q2. And do the same for firm 2. You get its revenue is price times its quantity, which is 1000 minus Q1 minus Q2 times Q2. Distribute the Q2, we get 1000 Q2 minus Q2 squared minus Q1 Q2, and then if you differentiate R2 with respect to Q2, you get MR2, which is 1000 minus Q2 minus Q1. So you should see the symmetry in the MR functions for the Carnot oligopulus. Okay, so now we're going to find the reaction function of both terms, which is set their proper maximizing condition, set that up, and then find the optimal Q1 star and Q2 star. So first we have term 1, MR1 equals MC1. MR1 is, you just found it, which is 1000 minus Q1 minus Q2. And then MC1, okay, so based on this, C1 is 4Q1. So if you differentiate that with respect to Q1, the MR is just 4. So both of the MCs are 4 because the cost function is just 4Q. So MC1 is 4. Okay, and then now let's just solve for Q1 as a function of Q2, which is going to define term 1's reaction function. So we get 2Q1 minus 1000 minus 4 is 986 minus Q2, and then divide by 2. We get 498 minus 1 half Q2. Okay, we're going to do the same now for term 2. MR2 equals MC2, which means that 1000 minus Q2 minus Q1 equals 4. And simplify here, we get 2Q2. We're solving for Q2. We get 2Q2 equals 996 minus Q1, and then divide by 2. And we get term 2's reaction function of 498 minus 1 half Q1. So again, notice the symmetry in the reaction functions where you get 498 minus Q2, 498 minus 1 half Q2. And 498 minus 1 half Q1 for both the terms. Okay, so we have both terms reaction functions. Now we're going to solve for both terms outputs by plugging the other term's reaction function into that term's reaction function. Alright, here we go. So term 1, 498 minus 1 half, plug in term 2's reaction function of 498 minus 1 half Q1. And now we get only Q1, but solve for Q1 to get term 1's output. We get 498 minus 249 plus 1/4 Q1. We get, subtract 1/4 Q1 from both sides. We get 3/4 Q1 minus 249, and then we get, multiply both sides by 4/3, you get 4/3 times 249, and this simplifies nicely to Q1 star of 332. Alright, and you should get the same output for term 2, but you have to double check. There you go, 498 minus 1 half, put it term 1's reaction function, 498 minus 1 half Q2. Okay. Q2 equals 498 minus 249 plus 1/4 Q2. We're solving for Q2. 3/4 Q2 equals 249. Multiply both sides by 4/3, we get 4/3 times 249, and you get the same result, where both Q1 star and Q2 star are 332. Alright, so we may have done it right so far, and the next step is to find the market price. Here's the demand curve, 1000 minus Q1 plus Q2. Plug in on both of our Q stars. Q equals 1000 minus 332 minus 332, which gives us the market price of 336. Okay, and then the last part is to calculate the profit for each firm, which should be the same, but you got to double check. So profit of firm 1 is its price, or it's the market price times its quantity minus its cost. So revenue minus cost. Alright, price is 336. Q1 star is 332, and the cost function for all the firms here is 4 times Q. So 4 times 332. And then that, you put this in the calculator, you get a profit of firm 1 of 110,224. And firm 2, same thing, revenue minus cost. And we get firm 2's profit is the price 336 times its output 332, and minus the cost function of 4 times its output 332, and you should get the same result for the Cornell oligopolis, where both profits are the same. In this case, they're both 110,224. So for Cornell, we get identical outputs, identical profits, and the market price is based on those two outputs. And so the point of this analysis is to compare this result with the Stackelberg result. So that's what we're doing now. Okay, so using the same demand function and the same cost function, let's now look at it from the Stackelberg perspective, where we have a leader and a follower, and the results can be quite different because of that, the nature of the industry. Okay, so this result, Cornell, was, like the game console industry. Now let's do the spreadsheet software. Where we get our example is Microsoft being the leader and Google Sheets being the follower. Let's do that in Stackelberg. Okay. The good news is we've already done some of the analysis from the previous Cornell part. So you already have firm 2's reaction function. It's going to be the same because the demand and cost function are the same. So firm 2's reaction function, we calculated that from the first part. Alright, so you can confirm that that's it, but you've already got this, so let's just stick with, we know that's going to be firm 2's reaction function, so let's state that for the Stackelberg version. Okay, and you already got the revenue of firm 1, so let's just put that there. So the revenue of firm 1, you got that right there. Okay, so you've already got two pieces of information you can use, which are R1, revenue of firm 1, and firm 2's reaction functions. We'll start with those, and we're going to do the rest of it. Alright, so you know that the first thing we want to do is do the leader first, which is maximize profit for firm 1 by integrating firm 2's reaction function into firm 1's profit maximization problem. Alright, so first we need to define profit, which is revenue minus cost of firm 1, R1 minus C1. Okay, you already got R1 right there, so we'll put that in. 1,000 minus Q1 squared minus Q2 Q1, and then all you have to do here is subtract the cost function, which is 4Q, so it's 4Q1. Okay, so we get 996 Q1 minus Q1 squared minus Q2 Q1. And then the next step is to plug in firm 2's reaction function into this Q2. So that goes here. Okay, because that's how firm 2 would react. And firm 1 knows that, so it's going to use that to choose its best profit maximizing output. So we'll simplify here. We get 996 minus Q1 squared minus Q1, and then plug in the reaction function for Q2 of 498 minus 1 half Q1. Do a little algebra. 996 minus Q1 squared minus 498 Q1 plus 1 half Q1 squared. And if you combine the like terms, you get 498 Q1 minus 1 half Q1 squared. Okay, so that is the profit function of firm 1. Let's maximize that with respect to Q1. Okay, and that means just differentiate the profit function, set it equal to 0, because that's when profit reaches its highest point, and then find the Q1 in which that is the case. So differentiate profit 1 with respect to Q1, you get 498 minus Q1. And when that is 0, that's when profit is at its highest, and it is just solve for the Q1. So we get Q1 star equals 498. Alright, so we have a few more things to do here. So let's find firm 2's output, the follower, by putting firm 1's output into its reaction function. Okay, so reaction function of Q2 is 498 minus 1 half Q1, and then we get 498 minus 1 half, putting Q1 star of 498, and we get firm 2's output is 498 minus 249, so it's exactly half, which is Q2 star of 249. Alright, the next step is to get the market price. So just start with the demand curve of 1,000 minus Q1 plus Q2 and put in the two output optimal decisions. Okay, 1,000 minus 498 is Q1 star minus 249 is Q2 star, and that gives us the price 253. Okay, and the last step for this analysis is to calculate the profits of both firms. You know that firm 1 is going to get a higher profit because it's the leader. So here's something like Microsoft's profit for spreadsheets. Its revenue minus its cost. Okay, price is 253. Output for firm 1 is 498. The cost function is 4 times Q1. So 4 times 298, and that simplifies to 124,002. So $124,002. Okay. And then for firm 2, its revenue minus its cost. Price was 253. Its output is 249 minus its cost. 4 times C, which is 4 times 249, and then its profit is essentially half of that, which is $63,001. Okay, so you've done the analysis, which you'll see that in the Cornell, both firms make the same profit. In the Stackelberg, firm 1 makes double the profit because it's the leader, and you can see that the lowest profit of all the firms is the firm 2 follower. And then you can also compare the market prices. So the market price in the Stackelberg was 253, and in the Cornell, 336. So given the same demand function and cost structure, it always turns out that the Stackelberg market's going to have a little bit lower price. Here's 336 for Cornell, and then Stackelberg is lower at 249. Sorry, 253. Okay, so that's the full analysis of comparing the two Cornell versus Stackelberg for this part. Questions on this?
No. We're good.
Okay. All right. So we're done with the PowerPoint here for chapter 9. So chapter 10 is on game theory, more oligopoly stuff, which we'll do after our little break. Let me bring up the homework for chapter 9, which will be next week. Okay, so here we go. So this is for chapter 9, this is the homework assignment. So this is something similar to what we just did, so you can use the notes and solutions and examples I gave you as a roadmap. So here's the homework for chapter 9, the next meeting, which is in 2 weeks. So all you're going to do is you have a Cornell versus Stackelberg analysis. So you're given a demand function and a cost function for the two firms. All right, and the first part is to do it from the Cornell perspective. So assume it's a Cornell market. Find firm 1's quantity and profit, firm 2's quantity and profit, and then the market price for the Cornell type. Okay, and then using the same demand curve and cost functions, do it from the Stackelberg where you have a leader and a follower, and find the leader firm one's quantity and profit, the follower firm two's quantity and profit, and then that market price. Okay, and then compare all the four markets, which of the four firms makes the highest profit and the lowest. Okay, and then part D is just of the two market structures. Which firm gives you the lowest price? You should get, the numbers will be different, but you should get a similar result in terms of comparisons, what we just did for the example. And so this one is your homework assignment for Chapter 9, and that's the next meeting in the appropriate discussion forum. Okay, which goes right there. All right, so that's the Chapter 9 material. That's the Chapter 9 homework due next time. So we still have Chapter 10 to do after the break, but I think that's what I wanted to cover for Chapter 9. All right, questions on what you have to do for this homework assignment? Okay, so we're halfway done with the oligopoly in today's material, so I guess we can take a break now, if that works for all you guys. So it's 10:03 now, so let's take a 30-minute break, and we'll meet back at 10:33.
Okay, thank you.
Thank you. Okay, hopefully everyone is back from the 30-minute break. So we got one more chapter to do on oligopoly, which is chapter 10 in your textbook. And so this will be on looking at some advanced game theory models and problems with oligopoly issues. Okay, so let's do chapter 10. Okay, so you can open up under the chapter 10 section. There's a chapter 10 Word document. There's a chapter 10 Excel file, and there's a chapter 10 homework. So I'm going to open up those three, and we'll get to those throughout the course of this session. Okay, and you can go to the PowerPoint, and we'll do the chapter 10 PowerPoint. Okay, so chapter 10, more oligopoly problems and issues, and this will be on game theory types. And there's a video, optional video there you can look at on your own time. Okay, so let's just start by some basic game theory. And so some of this you might have done a little bit of in Biz 500D, or if you learned any game theory issues in the past. We'll go into some more advanced models, but there's many more things you can do with oligopoly and game theory, but we'll look at quite a few examples. And so first, let's just define a few things. So a domino strategy is going to be, so we're going to have basically two players or two oligopolies, and they're going to compete in different types of models or games. And the outcomes of the games, or what the firms do, will help make important decisions or conclusions from what actually might happen in oligopoly markets, depending on the type. Okay, so just let's define first a dominant strategy. Okay, so a dominant strategy is just a strategy that results in the highest payoff to a player or oligopoly, regardless of the opponent's action. So that would mean they would choose that strategy every time. It's the dominant strategy, regardless of what the opposing firm or oligopoly does. So let's just get right into it. And we got a bunch of examples, but let's start with demonstration problem 10-1. All right, and so I did that on the Word document. Okay, so you got some optional videos to look at here. Oligopoly of the game theory, a little introduction. We haven't defined this term yet, but subgame perfect equilibrium, that's a little video more on that. And then we're going to get to sequential games in a bit, which means that one firm goes first and the other firm goes second. There's kind of a first mover advantage. All right. First demonstration problem, first example is demonstration problem 10-1 right here. And the game presented in table 10-1, which I replicated below, says player B has a dominant strategy. Remember, that means player B has a dominant strategy if player B would choose that strategy every time, no matter what the other player does. Okay, so here's the game, the payoff matrix, or whatever you want to call it. And so you might have seen something like this before. If not, we'll go through it quickly. So you have this game represents two players, player A and player B. So player B is on top in purple, and player B has two strategies. Go either left or right, and player A is on the left side, and player A has two strategies as well, going up or down, either one. And then the numbers you see in this matrix, if you want to call it, are the outcomes from both strategies resulting. So if player A goes up and player B goes left, this is the outcome, where the first number always goes to the left side, and the second number always goes to the top firm or player. So player A goes up, player B goes left. The outcome is player A gets 10, and player B gets 20. If player A goes up and player B goes right, player A gets 15, player B gets 8. Player A goes down, player B goes right. The outcome is player A gets 10, player B gets 10. And the final option, not a good one for player A. If player A goes down, player B goes left. The outcome is player A gets -10 and player B gets 7. So that's how you read this little game thing. All right, and then all you want to do here is determine which if player B has a dominant strategy, meaning would player B play that every time. So let's look at what player B would do in response to player A's two options. So if player A goes up, player B has two choices, which are to go left and get 20, or go right and get 8. So if player A goes up, player B would go left to get the 20 because it's better than 8. Alright, so I underline that there. And then, but if player A goes down, player B will go left and get 7. Or player B can go right and get 10. So in this case, player A goes down, player B is going to go 10. Right and get 10. So underline that there. So you can see that player B's response or best response depends on what player A does. Alright, if player A goes up, player B goes left. If player A goes down, player B goes right. So player B does not have a dominant strategy because it would not choose the same outcome regardless of what player A does. So no dominant strategy for player B. So let's just look at it from player A's perspective. If player B goes left, player A can go up and get 10 or down and get negative 10. Clearly, the player A will go up and get 10. If player B goes right, player A's options are up and get 15 or down and get 10. Again, player A is going to go up and get to 15. So for player A, it doesn't matter what player B does. Player A is always going to choose up. So therefore, player A does have a dominant strategy of up. So it doesn't matter what player B does, player A is going up. Player A has a dominant strategy of up. However, like we looked at, player B doesn't have a dominant strategy. Player B's choice would depend on what player A does, so there's no dominant strategy for player B, but player A has a dominant strategy of up. Okay, and then, so I did these game theory models in Excel because, in a classroom scenario, I would draw these up on the whiteboard, but I don't have that option at the moment, and so I did these kind of like templates in Excel. Okay, so I posted the ones that I did. Here's the chapter 10 spreadsheet. So when you do this for your homework or for the exams, the game theory ones, you can do whatever is easier or the best option for you to get the work done. You can use my Excel files as like templates and do it there, or if you prefer, you can just do it on my graphing paper and draw it with the ruler and just on a piece of paper, and then convert it to a PDF later. So if you want to do it in Excel, you're welcome to use my examples as a template or examples to use. Or if you want to do it just with a ruler and pencil, then we can do that as well. But here's what I did. Here's my Excel work for this one. So I basically just did it in Excel, and then I copied and pasted the result into the Word document. Okay, so there's the first one for the demonstration problem 10.1. All right, in which we just determined which players have dominant strategies and which do not. Okay, so everybody following along so far with the logic and what we've done just by talking about the games and determining dominant strategies. Okay, well, we'll keep building on these models, but if you have any questions, let me know. Okay, so building upon domino strategies in that same type of game where you have two players or firms and they both have two choices, let's define now a Nash equilibrium, and this is from the mathematician, economist John Nash. So John Nash is credited with this Nash equilibrium concept. The same John, if anyone's seen the movie A Beautiful Mind with starring Russell Crowe, which was came out like 20 years ago or something like that, but that the economist or the mathematician that Russell Crowe portrayed, John Nash, is the same guy who came up with this concept. Okay, so the Nash equilibrium concept is the definition here is a little confusing, but it's a condition describing a set of strategies in which no player can improve or pay off by unilaterally changing their own strategy given the other player's strategy. So that's true. Another way to think of it is just it's the outcome in which both players are choosing the best response. And there's usually only there's either one Nash equilibrium in these examples or zero. So if you find the case in which both players are playing their best strategy, that's the Nash equilibrium. So let's look at the same example again for demonstration problem 10.3. Okay, so in the game we just looked at, in the game presented in table 10.1, the same exact thing. Let's define the Nash equilibrium. So we went through all the players' best responses. So I underlined the outcome of what each player would do given the other player's options. One second. Okay, I had to let my dog inside. So here we did, okay, so we went through this. When player A goes up, player B goes left. When player A goes down, player B goes right, and vice versa. So I underlined the outcome of what each player would choose. And if you look at this, the way we did it, the Nash equilibrium is the only one in which both players are playing or choosing the best response. And another way of looking at that is if you underline it or circle it, it's the only cell in which both numbers are underlined. So basically in all these other options over here, those three, at least one of the two players would not choose that. The only outcome in which both players would not change their position is this one. So basically what happens is if both players have a domino strategy, then they both play the domino strategy and that's the outcome. But if only one player has a domino strategy, then the other player kind of assumes that, so it's not that hard to figure out the outcome here, that if player B doesn't have a domino strategy, what player B would do is say, I don't have a domino strategy, but player A does, and I know player A is going up. And so if player B knows player A is going up, then player B is going to choose its response to up, which is left. Okay, and so that is how you come upon the Nash equilibrium. It's the only situation, if any, in which both players are choosing the best response. If you do the analysis like I did, it's the one cell in which both numbers are underlined here. Okay, so given up and left, neither player can improve upon their position. So that's the Nash equilibrium, and you can describe it. Okay, like I did here, and what I did is if you want to describe the Nash equilibrium, you just list the two strategies and then the two payouts. So I usually do the left player first. So player A goes up, player B goes left, and player A gets 10, and player B gets 20. Okay, so make sure when you describe the Nash equilibrium, if any, you list the two strategies first, and then the payouts or the outcomes second. That's what we did here. All right, so the Nash equilibrium concept, everybody good on this? All right, let's keep going. Let's look at the Nash equilibrium concept in a more oligopoly-ish game. Okay, so a lot of things are common oligopoly game is an advertising situation. So a good majority of the oligopoly narratives that do games are looking at advertising decisions and pricing decisions. So we're going to look at advertising here. Demonstration problem 10-4, which will depict a hypothetical advertising game between two hypothetical oligopolies. Okay, so we've got the concepts of dominant strategy, and if both players have a dominant strategy, they're going to do that. If only one has a dominant strategy, then that player is going to choose it. The other player knows that, and they're going to respond to the other player's dominant strategy, and then whatever the result is, we can figure out the Nash equilibrium. Okay, so let's use this Nash equilibrium concept to look at an advertising game. Demonstration problem 10-4 in your chapter 10 text. Okay, suppose your firm competes against another firm for customers. You and your rival know your products will be obsolete at the end of the year and must simultaneously determine whether or not to advertise. In your industry, advertising doesn't increase total demand, but instead induces customers to switch among the products of different firms. So the demand is set by a certain number of customers, so advertising just takes customers away from the other firm and to yours. So you're fighting over the same pool of customers. So both you and your rival advertise the two advertising campaigns just offset, and you both lose money from the advertising budget, and each earn $4 million. If neither advertises, you each earn $10 million because you save the money from not advertising. But if you get a mix where one firm advertises and the other doesn't, then the firm that advertises essentially steals the customers away. And one of you advertises, the other doesn't, the firm that advertises earns 20 million, and the firm that doesn't just gets $1 million. So the question is your profit maximizing choice to advertise or to not, and how much money do you expect to earn? Okay, so first you look at the word problem and you define the game like we've been doing here. So you can set it up where both firms either advertise or don't, and the problem said that they both advertise, they both get 4. If they both save money and don't advertise, they both get 10, and if one advertises and one doesn't, the advertiser gets 20, and the loser, the non-advertiser gets 1. Okay, and the payouts here are symmetrical. So what you want to do is determine, we're basically defining a Nash equilibrium because there's no agreement yet. And so let's see what each firm would do in response to the other firm. If firm B advertises, firm A would advertise. Okay, because the 4 is bigger than the 1. If firm B doesn't advertise, firm A would again advertise and get 20 because if they don't advertise, they get 10. So no matter what, firm A has a dominant strategy of advertising. Okay, because this is bigger than this. And this is bigger than this. Alright, you can probably guess that firm B is also going to have the same strategy set, but let's do it from firm B's perspective. So firm A advertises. Firm B can advertise and get 4, or don't advertise and get 1. Firm B is going to advertise. If firm A doesn't advertise, firm B can advertise and get 20, or don't advertise and get 10. Okay, so we know what firm B would do there is advertise. So given the analysis, both firms have a dominant strategy of advertise, so that's what's going to happen. Now, you can see over here that if they both agreed not to advertise, they could both get 10 million and split that. That's a much better outcome. But the problem is, if they don't reach an agreement or trust each other, then these firms run the risk of only getting 1, and so they're not going to do that unless they can reach a exclusive agreement. Okay, so the outcome here is right there. You define the Nash just like this outcome. Alright, so you only cell in which both firms are finding their best response, and the only 2 numbers that are underlined in the same cell. So you can describe that. The Nash equilibrium here is both firms advertise, both firms get 4 million. Okay, strategies, then payouts, and then the question was, should you advertise or not? What do you expect to get? Okay, so your profit maximizing choice, is to advertise, and you'd expect to earn 4 million because that's what the Nash equilibrium result is. Okay, so for just a one-shot game, there's the Nash equilibrium best response concept used in practice. some type of oligopoly advertising scenario. Okay, so now we're going to look at games that are played more than once, or which changes things. So there's some multiple types of multiple types of repeated games. The first type we'll look at is this type, in which it's played infinitely, like you're assuming they keep playing the game, and that's how you model it. Okay, so infinitely repeated game is a game which is played over and over forever, in which players receive payouts during each play of the game. So you have multiple, like you have year 1, year 2, and you assume you keep playing the game infinitely. That's what this type of game looks at. Okay, so we're basically going to look at the game over a horizon and determine what the firms would do if they had the chance or the opportunity to reach an agreement, and given that, will they keep the agreement or not? So let's look at in terms of present value terms, because we play this game over and over. You know that the payouts received in the future are worth less based on some interest rate. So we look at present value analysis and determine what each firm would do in a game like this that you play over and over. So let's look at an example of demonstration problem 10.6. Actually, let me show you the present value formula again for this concept. Okay, so we did present value on chapter 1, and we did it on the midterm as well. So let's use that concept here, where here's the present value for a firm. If the profit or the payout is the same each period, you just sum them all up and you discount them. Right? So here's period 1, and there's year 1. There's the next period. Right? You have to discount it just like we did with present value, divided by 1 plus I, and then if it's another year, you discount it with 1 plus I squared, and then so on. So we've done the same concept when we calculated present value. So we use that here when we're looking at the stream of payments over kind of an infinite horizon. But because your present value is the sum of all these profits discounted like this. But if the payment is the same exact payment for the whole time and the interest rate is the same, then you can simplify this calculation to this. Where if the profit's always the same and if the interest rate's always the same and it's played infinitely, then your present value can be estimated or assumed to be 1 plus I divided by I and times that profit you get every single year per period. Okay, if the profit changes, if the profit is not the same, you can't use this, but if it is, you can. Okay, and so let's look at this in practice in an example. All right, demonstration problem 10-6. Okay, so there's I put the general formula if, and remember this is only if profit is the same every year and if the interest rate is the same every year. Okay, let's suppose that firm A and firm B repeatedly face the situation presented in table 10.7, which are replicated here, and the interest rate is 40%. So this is a very high interest rate, so this is going to affect things. Okay, so the firms agree to charge a high price each period, provided neither firm has cheated on this agreement. And so what you see here is that instead of just coming up with a Nash equilibrium, so look at this game here. Okay, so if each firm, if they didn't make an agreement and they played this game forever, then the result would just be the Nash equilibrium multiple times. So see, like if you look at it from best response, if firm A goes low, firm B can go low and get 0 or high and lose 40. So firm A is going to go low. And if firm A goes high, firm B could respond by going low and getting 50 or going high and getting 10. And so you can see that both firms, if you do the analysis like we did before, with no agreement, both firms will have a dominant strategy of going low, and the result will be this. Yeah, that's the Nash equilibrium. But you can clearly see if they play this game, especially multiple times, that they can both get 10 every time if they agree to price high instead of low. Okay, so this is a firm oligopoly market with two firms. If they both price low, they just get less revenue. But if they both agree to price high, the customers have no choice but to pay that price, and therefore the revenue of both firms increases to 10. So if they can agree both to price high, then both firms are better off for the whole infinite horizon of this game they play. Okay, but you can also see that there's a trade-off, or there's a incentive to cheat for some of the firms. So what we're saying here is that the profits are either they agree to both price of 10 or both price high, and they get 10 every time, the profit of 10. Or if one of the firms cheats, on the agreement and gets 50 and the other firm loses 40, then anytime there's one of the firms cheats or breaks the agreement's over. And then for the rest of the time horizon, the profits go back to the Nash equilibrium, which is no agreement. Okay, so we need to figure out if it's more profitable for the firms to keep the agreement, or if it's better for them to cheat one time, and then even though the agreement breaks, it's worth it for the one-time cheating. So we need to calculate a profit for both firms, or just pick a firm because it's the same. So what's the expected profit if it cooperates and gets to 10 every time? Or what's the expected profit if they cheat and get to 50 and then the rest of the time they get 0? Okay, so what are firm A's profits if it cheats on the exclusive agreement? Remember, the agreement is that they both price high, they both get 10 every time. If the agreement is broken, the agreement's over. So cheating is essentially ending the agreement. Is it worth it? Let's see. Alright, so the present value of cheating. So because the payout changes if you cheat, so because it's being played over and over, if you cheat right away, you get this first. And then for the rest of the times you play the game, you get 0. So the profit, you can't use this exact formula for cheating because the payout changes. So that can only be used if the payout's the same exact thing every time. In this case, it isn't. So we can figure out it's easy to see this because the other outcome is 0. So basically, if the firm cheats, they get 50 right away, and then a bunch of zeros because once the agreement's broken, it's over. And so it's basically like if you sum up 50 and a bunch of zeros forever, the total is going to be 50. So it's 50 plus 0 plus 0 plus 0, a bunch of zeros, which is just going to be 50. So the present value of cheating is the 50 now, and then a bunch of zeros added to that, which are just 50. Okay, and so we're not going to do an example for the infinite games in which the Nash equilibrium outcome is not 0 because it complicates things. But note that if this outcome were not 0, you couldn't just do the same thing. So you would have to, if this outcome were not 0, you would have to add in the one-time cheating plus the discounted profit of the Nash equilibrium other result. And so the calculation I did here, it comes out to the right answer, but I noticed that this portion is not exactly correct because you can't use this formula unless it's the same exact profit every time. So I put a few, I just wanted to clarify this, even though we don't really have to do it for this course. But if you were doing this analysis and this number wasn't 0, you would have to compare the cheating by using a discount factor. And so I put a couple of links just to show you, like, to make sure that this was clear, of what you would do in another scenario in which it wasn't 0. So alright, so if you go to the chapter 10 section on Blackboard, I added a few links just to clarify that the difference here, even though this is not required. But so if you click on this, links for repeated games. Okay, so again, you don't have to do this for this class, but just to clarify what you would do if you had a scenario in which the Nash equilibrium result was not just a bunch of zeros, you'd have to calculate the discount factor. You're probably familiar with the discount factor, but the discount factor is just 1 over 1 plus r. Okay, and then use the discount factor to make comparisons. And if you want to see how this is done, I put up a video. We're not going to watch it, but I just wanted to show you what I mean here. Okay, so if you can see this here, then this explains what you would do if you had to calculate a cheating scenario in which the payout was not zero in the future period. So look, here's D is the discount factor. Okay, so it's basically the discount factor over 1 minus the discount factor goes here. And the formula works fine for this side because in this example it's the agreement is 50. So for us it would be 10. So you can just use the simplified example of the present value. Okay, but if cheating were different, so over here, the cheating, they get 60 the first time, and then 30 the rest of, so when the agreement is broken, it's not 0, it's 30. So if you had a situation in which you had to calculate cheating for an infinite game, and the Nash equilibrium was not 0, you would do this. So for us, to calculate it, to technically calculate it, you would put 50 there for the one-time cheating, plus 0 over discount rate divided by 1 minus the discount factor. Okay, so, and the discount factor D is 1 over 1 minus R. So it gets a little more complicated, and we're not going to do it for this class, but I just wanted to show you that I'm putting a 0 here because we simplified the problem to be the Nash equilibrium is when the agreement is broken, they just give 0 for the rest of the time. But if it didn't give 0, like if it was 1, you would have to put in the 1 here and do the one-time cheating plus the Nash equilibrium from, when the agreement is broken, and then this discounts that. So we're basically, to really understand what we're doing is you're doing either the first game is discounted because it happens right now. So this is, in this one, the 50 is cooperating, and the 60 is cheating. And then if you keep cooperating, you get 50 for period 2, and then this discounts it for the rest of the time. And if you cheat, you go back to the lower amount, and then you have to discount this. So I just wanted to clarify that if you wanted to, if this came up and you wanted to do it and you didn't have 0, you would have to use this discount factor analysis. Okay, so in summary, I'm just telling you that the formula I put here is technically mathematically incorrect, but it's right for the zeros. So if you really want to do this correctly, you'd have a 0 times 1 over 1 minus the discount factor. Okay. So sorry if that was confusing, but I just wanted to clarify that if your Nash equilibrium is not 0, then you got to use that discount factor analysis that I just talked about. Okay, so doesn't matter for year because if the player cheats, he or she gets 50 and then a bunch of zeros, so the total is going to be 50 for cheating. And because the cooperating scenario is always the same payout, you can use this simple formula, which is just the profit of 10 times 1 plus the interest rate divided by the interest rate. Okay, so what a firm A's profits if it does not cheat on the agreement, and so that would be 1 plus the interest rate is 1.40 because the interest rate is 40%, and then divided by the interest rate is 0.40 for 40%, and then times 10 that the firm gets from cooperating. So we're just using this formula. Okay, and this comes out 1.4 divided by 0.4 is 3.5. And times 10 is 35. So if they cooperate, the expected payout is only 35, and that's because the discount rate is, and the interest rate is ridiculously high at 40%. And so we're saying that if the firms had an incentive, they could cheat now and take the 50, and then earn 40% interest on that 50 for the rest of the time, and that would be more valuable to the firm than cooperating and giving up, the interest earned. So the present value of cheating is 50. The present value of cooperating is 35 because the interest rate is so high. And so does an equilibrium result where the firms charge the high price and cooperate? So no, they don't, because the expected values in cheating is 50, which is bigger than cooperating in 35, and then basically both firms are just gonna see that and price low, and they're both gonna get zero. So present value of firm A's profits is higher if it cheats, and if it doesn't cheat, and the matrix is symmetric, so each firm has an incentive to cheat, which is probably what they're gonna do. So each firm is gonna charge a low price each period, and then the result will be just back to the Nash equilibrium of low, low, 0, 0. So all we're doing here is comparing the expected outcome from cheating, the expected outcome from cooperating, and whichever one gives us the highest expected result is what the firm would do. Okay, so questions on this one? Hopefully I didn't confuse you with the tangent of the present value of cheating, but I wanted you to understand the full calculation of what you would do if you had a different 0, 0 result. Okay, the next type of game under the repeat games type is a finitely repeated game. So this is a game that's going to end, but you don't know exactly when. And there's a probability you calculate of when the game's going to end. Okay, so we're going to look at a repeated game in which there's an ending period, but you put probabilities on when the game will end. All right, everybody doing okay so far? Okay, so let's look at how the probability of the game ending plays in here. Okay, so we're going to use a simple term called theta, and in this example, theta is going to be the probability that the game will end after a given play. So this will help us determine the number of times we expect to play a game, and then we're going to use that theta to determine the expected outcome of cooperating. And so basically, it comes out nicely that if you get the same payout every time for cooperating like you do, then it's just that number divided by theta, and you'll see that it exactly correlates with the expected number of times you think you're going to play the game based on the probability that it will end. So let's look at this in practice. In demonstration problem 10.7. Okay, so two cigarette manufacturers repeatedly play the following simultaneous move billboard advertising game. Alright, so now we're looking at, again, an advertising scenario in which both firms benefit from that advertising if they can agree, but advertising is costly, so it just cancels each other out. But then if one firm advertises and the other doesn't, they steal too many customers away. And so that's the game that's going on with these oligopolies. So both firms advertise. Each earns profits of 50 million. If neither advertises, each earns profits of 10 million. And if one advertises and the other doesn't, the firm that advertises earns 20 million, and the firm that doesn't advertise loses $1 million. That's a -1. Okay, and then the thing here is if there's a 10% chance that the government will ban cigarettes in any given year, can the firms collude by agreeing not to advertise? Okay, so we don't know exactly when the game's going to end, but there's a 10% chance the game could end any period. Alright, so we have to use that as our theta. This theta is 0.1 or 10%, and factor it in. So we can basically expect to play the game 10 times because if the probability of it ending is 10%, your expected number of rounds is 1 divided by theta, which is 10. Okay. So here's the game that the word problem describes. The outcome if they both advertise, the outcome if they don't advertise, and the outcome if one advertises and the other doesn't, then it's a 20 minus 1 scenario. Okay, so you can do the analysis, and if you just did the Nash equilibrium, they both advertise because they don't want to risk losing the -1. So this would be the Nash equilibrium if you did the analysis. But you can clearly see there's an advantage or benefit to cooperating, and if they both cooperate, they both get 10 million instead of 0. Okay, so if these firms can agree to save their advertising budget and they both don't advertise, then instead of they're spending the $10 million on advertising, they get to keep it, and both firms earn 10. So this is the outcome each time if they both keep this agreement and agree that it's better to not advertise. So let's see if they'll keep this agreement of 10 every time, don't advertise, or if there's an incentive for one of the firms to cheat. If there is, then both firms will cheat, and they'll both go back to the national equilibrium outcome. Okay, so what you have to do here is calculate based on the theta the expected number of times that this game will go on. So it goes on for a number of times, but there's a 10% chance it will end any period. So to calculate the number of times you expect to play it, just 1 divided by theta is the number of, let me just put that here. Okay, so if you look at the chart, 1 divided by theta is the expected number of times that the game is going to be played. So if your theta changes, then your expected number of times to play the game changes. But you can probably see that if there's a 10% chance the game ends, then the most likely scenario is that you play the game 10 times, and then that's the expectation. Alright, so another way to do that is simply just 1 divided by theta. So 1 divided by 10% or 1 divided by 0.10 is just the number of times 10 that you think this game will go on. Okay, so you have to do that for the cheating scenario because the payouts are different. Okay, so if we expect to play the game 10 times and we cheat, that means the one-time cheating, you'll get 20. Okay, and then the other 9 times you'll get 0. Now, it comes out easily to 20 here because this result is 0, but you can do it if this is not 0. Okay, so there's the one-time cheating. There's the other 9 times you expect to play the game, but the agreement's broken because you cheated, and so you just get 0 for 9 times, and so the total expectation of cheating is 20, which is 20 million. Okay, if you cooperate, you can use that formula, which is just the profit divided by theta, because the profit's always the same each period, or you can confirm by calculating the number of times you expect to play the game, which is 10, and multiplying that by the cooperating outcome. So cooperating is either that profit divided by theta, which is 10 divided by 0.10, which is 100 million, or just double check and make sense that if you think you're going to play the game 10 times and you get 10 every time, then cooperating gives you 10 times 10 times, which is 100. Okay, so you can double check that your cooperating outcome is the same by using this formula. Or by just taking the outcome of cooperating and multiplying it by the number of times you expect to play the game, which is 10. So 10 divided by 1.0.1 is 100, and also 10 times 100, 10 times 10 is 100. So if you play the game at a number, you can expect to play it 10 times. The present value of cheating is 20 plus 9 zeros, which is 20. But if you expect to play the game 10 times and cooperate, you get this outcome 10 times, which is expected to be 100. So that's a much better result than cheating. So since 20 is less than 100, the firm has no incentive to cheat, and the incentives of the other firm B are symmetric, and so both firms will see this, and they're going to collude, keep the agreement, price agreed is not advertised, and then they're both going to get 10 plus 10 plus 10 for 10 times, which is 100, and that's a much better outcome than trying to cheat once, and then losing what you would have gotten from cooperating and just getting 20. Okay, so questions on what we did here with the theta addition and playing the game a number of times, but knowing it's going to end based on the theta metric? Okay, we see how we got the cheating and cooperating given the theta. Okay, so there's one more type of repeated game, which is a repeated game with a known, so you know you're going to play the game a certain number of times, like 10 times. And this results in an end of period problem, where it just comes back to kind of a Nash equilibrium outcome. And so to see this concept, let's look at demonstration problem 10.8. Okay, let's suppose that you and your rival played the game in 10-11 two times. So suppose your strategy is to charge a high price each period, provided your opponent never charges a low price in any given period. And what do you earn? Interest rate is 0. So here's the problem with this known final period. Okay, so if you do the Nash equilibrium, you're going to get low 0 0. So you can see again, if they can reach an agreement, they can both get 10 every time. Okay, now the problem is this game is known to be played 2 times. So from a total profit or best outcome scenario, you can see that the best thing to do for a firm would be to make the agreement, keep it one time, and then cheat the second time, which would give you 10 plus 50, which is 60. Okay, so there's the agreement. So if you play the agreement 2 times, both firms get 20. But if you play it once and cheat, you get 10 plus 50, which is 60. Now the problem is that both firms will figure that that's the thing they should do, And if the final period is known, both firms are just going to shoot right away, and it's going to go to this result. Okay, so this describes it here. So given your strategy, your opponent's best strategy is to charge a high price the first period, keep the agreement, and a low price the second period. So if you charge a high price each period, you get 10 plus 10, for a total of 20, that's the full agreement. But if you charge a high price the first period, you get the 10, and then shoot, you get 50. So for a total of 60. Alright, but you can see that 10 the first period and losing 60 the second period for a total loss of 30. But you both know that this is the best result. So instead of this happening, you're both going to jump the gun and just charge low because you don't want to risk one of the firms cheating and losing 40. Okay, so the conclusion here is that if the final period is known, if you know you're going to play it 10 times or 5 times or whatever, then the outcome is just going to be the Nash equilibrium, which is this case here. Okay, so we have another type of game which is a little bit different, and these are going to be called multi-stage games. And this is going to be a game in which there's a first mover advantage, or like it's sequential. So one player is going to go first, and another player is going to go second, and that's going to make a big difference. And so we'll kind of illustrate the game a little differently because we're going to draw like a little game tree, and there's going to be a first mover advantage that we'll see. So all of the examples we just did that I did in the demonstration problems, okay, you can find my Excel work in the Chapter 10 document. So here's demonstration problem 10.1 and 10.3. There's 10.4. There's 10.6. Here's 10.7. There's 10.8, and then these two we haven't got to yet. Okay, so again, you're welcome to use my Excel as a template or example. If you want to do your homework and exam questions in Excel, or if it's easier for you to do it that way, you can use drafting paper, etc. Okay, so everybody following along? All right. We'll start the multi-stage game. So here we got let's define a different type of equilibrium that you use for sequential games. So this is called subgame perfect equilibrium. So this is a condition describing a set of strategies that constitutes a Nash equilibrium that allows no player to improve his own payoff in any stage of the game by changing strategy. So it's a full list of best responses by both players, given the nature of the game. Okay, so don't worry about the big words, but I'll show you how to describe it after we develop the game. So now we're going to look at two examples of sequential games in which one player goes first and the other player turn goes second. And these are called multi-stage games or sequential games. So demonstration problem 10-9. Let's look at that one first. Okay, so here we go. So you read the little description and it'll kind of tell you how to illustrate or depict the game for this type. So your firm must decide whether or not to introduce a new product. If you introduce a new product, your rival will have to decide whether or not to clone the new product or not. If you don't introduce a new product, you and your rival will each earn, or if you don't introduce a new product, you and your rival will earn $1 million each. If you introduce a new product, you and your rival, if you introduce a new product, you will lose $5 million. Oh, sorry. Okay. Sorry about it. So here you go. If you don't introduce it, the game ends. You both get $1 million. If you do introduce it, then your rival player B has an option to clone it. So if you introduce it and your rival clones it, you lose $5 million and your rival earns 20. Okay, so you lose all the research and development budget, and your rival pretty much just like steals the recipe. Okay, the other third outcome is if you introduce a new product and your rival doesn't clone it, you get $100 million and your rival gets 0. So first, set up the extensive form of the game, which is just draw the game tree, and then let's determine if you should introduce a new product. So basically what we're going to do is draw the game tree and define the equilibrium. Okay, so here's based on the word problem. Player A goes first. Player A has two options, introduce or don't introduce. Okay, if player A doesn't introduce, then player B has no choice. The game just ends, and here's the outcome. The first number goes to player A, the first mover, and they both get $1 million. Now, if player A doesn't introduce, then player B has a choice. Okay, player B can clone, in which the result is player A loses 5 and player B gets 20. Or player B should don't clone, not clone, and then player A gets 100 and player B gets 0. Okay, so what you want to do in this type of oligopoly game for these firms is you want to go to the second mover for the last player and start from there. So you kind of do this like, it's called backwards induction. Or go to the end of the game and then solve it backwards. So let's go, so if the second mover had a choice of clone and don't clone, let's see what they would do. So if player B was given a choice, player B could clone and get 20. Or player B could not clone and get 0. So if player B gets the choice, it's pretty clear that what player B is going to do is to clone it and get 20. So if player B gets a choice, player B's clear best option is to clone and get 20. Highlighted that. Okay, now the thing is here that player A gets to go first. So player A has the first mover advantage of seeing what player B would do and making its decision first. So player A knows if player B gets the option, player B is going to clone. So if player A reduces, player B is going to clone, and then player A loses 5. The other option is player A just doesn't introduce it, and player A gets 1. Okay, so you can see the two future results of player A. If player A introduces, player B clones it, -5. If player B doesn't introduce it, it gets 1 million. So it's obviously better to not give B the choice and just still introduce the product because 1 is much better than -5. Okay? So the outcome is this highlighted result here. Where player A has a first mover advantage and player A, it's done the calculation, it's not going to give player B the choice. Its best outcome is just to not introduce it, not get it stolen, and just take the 1 million. Okay, and you can describe this outcome, which remember is called the subgame perfect Nash equilibrium, or SPNE. And all you have to do is describe the strategies of the two firms and then the outcome. So player A is best choice, his or her best choice is to don't introduce. And even though player B didn't get to choose, they would always choose clone. So we'll always put player B's choice regardless. So player A is always going to don't introduce. Player B is going to clone, and then the outcome though is 1 million, 1 million. Okay, and so you should not introduce a new product because the one you get introduced from not introducing is better than the -5 from getting cloned on. Okay, so here I did this game tree in Excel. If you want to use that as an example, or again, if it's a better option for you to just illustrate this on with pen and paper, you can do that too. Okay, so questions on this one where you got to draw the game tree and there's a kind of a sequential game going on. All right, everybody's good. All right, let's do another example of a multi-page sequential game. Demonstration problem 1010. Okay, here we go. Instead of the bargaining game just described, let's suppose the order of players reversed. The union gets to make an offer, and then management decides whether to accept or reject it. What's the subgame perfect Nash equilibrium outcome of this bargaining process? Okay, so there's an example in textbook, and this we just flip it around. So let me just show you what we're starting with here. Okay, so here you see in figure 10, the first example was this, in which we're trying to determine how to split $100 between management and the union. But in the first example, the management goes first, and we simplified to saying they offered $1, they offered 50, or they offered 99, and then the union gets to respond, either accept or reject it. Now, the example we're looking at is the same, except the union goes first and management goes second. Okay, so here's the game here. U is the first mover of the union, and we simplified the splitting of $100 to either $1, 50, and 99 to get the idea. Okay, so the union offers something, and so the offer means if they offer $1 to management, the management gets the dollar, and then the union gets the rest. So, and then if the management accepts it, then the offer is realized. If they reject it, both firms get zero, or both parties. Okay, so if union offers $1, management can accept it, and that means that they get $1, and the union gets the rest of the 99, or reject it, and both firms get zero. Okay, if the union offers 50, the management can accept it, and both get 50, or reject it, and they both get zero. Okay, the third scenario is the union offers 99. Management accepts it, they get the 99, and the union gets the $1, or reject it, and they both get zero. Okay, so the first number always goes to the first mover, which is the union. And the second number in the payout always goes to the second mover, in this case, which is management. Okay, so look at the second mover's option first, and then the first mover of the union is going to look at that and make its decisions based on its first mover advantage. So the union knows or can calculate what the second mover, the management, is going to do. So if the management gets this offer, they can accept it and get $1, or reject it and get zero. So you can see that accepting $1 is better than getting nothing, so they're going to accept. If the management gets this offer of 50, they can accept it and get 50, or reject it and get zero. So again, they're going to accept it and get the 50. Okay, if they're given this other option of 99, they can accept it and get 99, or they can reject it and get zero. So again, they're going to accept it and get the 99. So what you see here is that no matter what is offered, their management's best response is to accept it, because if they didn't accept it, they would get zero. So no matter what is offered, the second mover is the management's best response, or what they're going to do, is accept. So the management's always going to accept, because accepting something is better than losing everything. Okay, so the union can see that what the management's always going to accept. So the union's best thing is to offer the most the best that they can get, because it'll get accepted no matter what. So if they offer $1, it gets accepted, they get 99. If they offer 50, it gets accepted and they get 50. If they offer 99, it gets accepted and they get $1. So everything's going to get accepted, and you can see they're choosing from $1, 50, and 99. So they're going to, if they have the option, they're going to offer, because they have the first mover advantage, they're going to offer $1. That gets accepted, and they get 99. Okay, so the first mover advantage makes a huge difference here because everything gets accepted, because if it didn't, it would just get 0. Alright, so you can describe this outcome is what each player would do, and then what the result is. That'll be your SPNE. Okay, so the first mover, the union, is going to offer $1, so that's, they know it's going to get accepted. And then no matter what, the manager is always going to accept that your outcome is going to get either highlighted one where the union gets 99 and management gets $1. Okay, so with these ones, just describe the strategies of both the first mover and second mover, and then the outcomes that the game results in. Okay, and then here's what I did in Excel for this one, if you wanted to look at that in the Chapter 10 Excel file attachment. Okay, so I think those are all the main types of examples and game theory models we're going to look at in Chapter 10 for the oligopoly game theory analysis. So questions on any of these so far? Okay, so here we go. Here's the homework assignment. I think it's one big question for Chapter 10. So here's what you're going to do for this one. So you have an example. You have like a little word problem, and you're going to set up the payoff matrix. Okay, so you have two oligopolies, Toyota and Hyundai, playing a pricing game in an oligopoly game theory aspect. Okay, so first you're going to do the one-time game, draw it, and define the Nash equilibrium. Okay, then the second part is you're going to assume they play a uncertain number of times, but the probability of the game ending is given by theta. And so you have to determine what I guess it doesn't matter which one you look at, but for Toyota, because they're here player one. So what is Toyota's expected profit if it keeps, and if it keeps the agreement? Okay, and then the part C is a sequential game scenario in which Toyota makes a decision, and then Tesla goes second, and so you just got to draw the game tree and then determine the outcome of this game. Okay, so one question here, 3 parts. And what we did here is similar, very similar to the analysis we did in the demonstration problems. And you can look at my examples if you need those. And the only, let me see. So make sure you, for part B, make sure you understand the theta scenario. So determine the expected number of times you're going to play the game, and then use that to determine your outcome, because the default, the Nash equilibrium is not just 0. So you have to calculate the number of times, do the same exact thing we did in the example, but when they choose, they get something, and then the rest of the number of times they get the other outcome. But I don't think it's 0 here. I think it is 1 million. Okay, so the cheating scenario is the cheating plus a bunch of 1 million, so you have to determine the number of times they think they're going to play the game based on the theta. Okay. Questions on what you have to do for the homework? And again, you're welcome to do this in Excel like I did, or you can do it on with pen and paper if that's fast. If that's whatever's best for you given your current technology situation. Okay, so any questions on what you have to do for the homework for chapter 10? Okay, so let me sum up what we're gonna do here. So for today, make sure if you haven't done so already, make sure you submit via email your midterm exam to me. So most of you have already done that, but make sure you get your midterm sent to email today. Make sure you get your chapter 8 homework into the discussion forum here. That's due today as well. So today you're gonna, if you haven't done it, chapter 8 homework and midterm. For next time in 2 weeks, you have the chapter 9 homework and the chapter 10 homework both due here and here by sometime in the next 2 weeks. Okay, so this is due today. This is due today, and then next week you're gonna put in your homework problem for chapter 9, your homework problem for chapter 10, and so everything we're up to date on the syllabus. The dates are all the same, and then during our last meeting, we're going to have another longer kind of project homework called the oligopoly homework, so we'll do some data analysis in Excel again. Okay, and then also next time, we'll do another review session for the final. So I'll prepare a practice exam. We'll go through that. That'll be a review session. Then I'll give you guys the final. And then just note that you have a little less time because I want to get the grades in. So make sure you plan out time to do these 2 assignments, which are both due. Everything is due. The very last day, the very last possible time to turn in anything is August 13th. And that'll give me a couple more days to get your grades in by the 15th. Okay, and then I'll also get this video up sometime today. So you can refer to that if you need to, or any of the oligopoly, Cornell, stockholder, game theory examples that you guys are for the homework. Alright, so it's about 12:15. I think we've done what I want to do for today, and I think you guys have plenty of things to do. Any questions on anything before we wrap it up for today? Okay, I think that's going to be it for today. You guys know what's due today, what's due next time, and so on. If you have any questions or need help, you can email me. And otherwise, that's all I got for today. And I'll see you guys for our last meeting in 2 weeks, same time, 8:30 in 2 weeks. But thank you guys for participating, and please stay safe.